Okay, I'm going to get started now. How you guys doing? Pretty good? Yeah, are you guys ready to glue today? My name is Mehul Shah, and today I'm going to be showing you how you can build data transformation pipelines with AWS Glue. I'm a manager on the service. I'm going to take my jacket off, it's a bit too cold or hot around here. So today, I'll be giving you a quick introduction to AWS Glue. I'll start diving into how you can construct an ETL flow in Glue from raw, unfiltered data to an ETL flow running in production in 4 easy steps. Then I'm going to actually dive into the underlying features that Glue provides that makes this actually possible. And hopefully you'll learn how to customize your own AWS Glue scripts by listening to this talk. And in the latter quarter of this talk, I'm going to ask one of our early customers, Merck, Keith Smola over here is going to be speaking for them. And they'll relate to you some of their experiences in using Glue and how quickly and how easy it was to get a ETL pipeline running in production. They were able to do it in less than a week. So what is Glue? Glue is a fully managed, serverless, extract, transform, and load service, or ETL for short. Now there are plenty of ETL tools out there, but Glue is one of the few that's designed for developers and built by developers. We've got thousands and thousands of customers on our platform running thousands and thousands of jobs on a daily basis. Here are some of our customers today, some of our early customers, and as I said, Merck will be speaking about their experiences using Glue at the end of this talk. In our ecosystem in AWS, we actually have a number of partners that do ETL. There are many tools already available. It's just a smattering of the ETL tools shown on the Redshift partner page. But it turns out that our customers are still developing a lot of ETL by hand, by actually hand coding their ETL. Why is this? This is the reason, by the way, that we built Glue. Okay? It's because every one of these tools that I showed you in the previous slide does something extremely well, does that one thing extremely well. Okay? But your ETL job in your organization or in your company isn't just about that one thing. And when you want to go beyond that one thing, typically you end up having to build it on your own. And that's why you use code. Code is powerful, it's flexible, you can do a lot of things with it, and there are very little limitations to code. Code is modular. You can actually build it in a way where you can share it with your friends across your organization. And more importantly, your organization already has a bunch of developers that know how to deal with code. They're building applications for you. They have a pipeline in place for managing and developing code. So why not manage and develop your ETL scripts and your ETL jobs the same way? There are familiar tools there, IDEs for debugging and editing. You've got version control for tracking changes. You've got a testing pipeline, continuous integration and deployment, and so on. And so in this talk, I'll be speaking to all the developers in the room over here. I'll be describing some of the core data structures and algorithms that AWS has, the IP it has internally, that'll help you make your life a lot easier. And if you're not a developer, hopefully you'll walk away knowing a lot more about the underlying IP that we provide that powers your ETL jobs today. All right, so even though everybody's coding, that doesn't mean coding is easy. In particular, writing ETL code is especially hard. And the reason it's hard is because the underlying data is changing. It's changing very quickly. The underlying data structures, the schemas are changing, the data formats are changing. As you often, in an agile environment, need to add or change the sources that you have, and the data grows. It grows pretty fast. And so what this means is that developers have to constantly change and adapt their scripts, and it makes hand coding extremely error-prone and brittle. So what does AWS Glue do? it actually does a lot of the undifferentiated heavy lifting that you need to manage these changes, so that developers can focus on the high-level things that they want to get done for their ETL code, and we do the rest underneath. All right, so that's sort of the premise for AWS Glue. Let me kind of walk you through the three main components of AWS Glue. First, we have a data catalog, and it's there for helping you discover and understand the data sources that you have. We have crawlers that are associated with data catalog that when you point them to your data sets will automatically extract the structure and store all that information, including statistics, into the catalog for you. The catalog is Hive Metastore compatible, which means it is now, you can integrate it with a lot of various tools, including a number of AWS analytics services like EMR, Athena, Redshift Spectrum, and so on. The second component is the job authoring and ETL system. And that's what I'm mostly going to be talking about today. The first thing it does is it actually lets you get started quickly with a ETL flow. It generates code for you if you point it to tables inside of the data catalog. The code it generates is in a familiar language, Python, and particularly PySpark, that works with Apache Spark underneath, vanilla Apache Spark. So it's an environment that many developers are already familiar with. And then we offer tools that allow you to edit and debug your code, as well as explore the data sets that you want to go and analyze. We also have a number of new and interesting primitives that make this easy, and that's what I'll be talking about today. The third thing that we provide is a job execution system that's serverless. You give us your code, your ETL code, we turn it into a job, and then we run it for you. You never have to spin up any machines, manage their life cycle, configure them. It's basically give us and go. You can also schedule these jobs in a very flexible way and monitor their progress. All right, so what are people using Glue for? What are our customers doing with Glue? One of the main things that they're doing is actually loading data warehouses. They get all their data from a variety of different places, integrate it together with AWS Glue, structure it, and then put it into Redshift, so then you can analyze that data later. Another thing that they do is they actually are trying to build data lakes with Glue instead of warehousing their data. Here, they'll crawl all their data, index all their information, and then make that data available and ready for analysis through one of many analytics services that we have, EMR, Athena, and Redshift Spectrum, including a bunch of other BI tools that work on top of them. All right, so now given these components, I'm going to show you how you can construct an ETL flow in 4 easy steps. The first step is to simply point the crawlers and data catalog to your data, and the crawlers will automatically figure things out for you. I'll give you an example of that shortly. Next, once you have your data all kind of indexed inside of your catalog, you can specify mappings with the AWS Glue console that will then generate an ETL flow. It'll actually generate some code for you. You can edit that code using development endpoints in an environment which is exactly the same environment that you get when you run your jobs. And then finally, you can schedule and trigger your jobs in a dynamic fashion. Now, you don't have to do all of these things to get started. You can just do one of them. For example, just catalog your data and start using an analytics service. Or you can just use the underlying Python and Spark infrastructure that we have. The point here is that we have all the primitives that you need to go from raw data to a production job. Now, throughout this talk, I'm going to be working with a specific example where we convert a bunch of JSON data from JSON to CSV. It's a typical process that you see in both building data lakes as well as loading data warehouses. And so it's a canonical example that you can take home and try out yourself. The example here is going to be working with GitHub archive data. This is basically the archive of all the events, the public events that GitHub makes available for you online. They actually generate these files on an hourly basis and make them available, and you can go download them and analyze them. God bless these guys, because there's a lot of wonderful public data there. You can grab that data through a variety of mechanisms. In this case, what I've shown you is you can go and download it through AWS Lambda and put it in an Amazon S3 bucket. You crawl it using Glue crawlers. They'll reconstruct the structure. You convert the data using our ETL system. And then the output is actually put back into Amazon S3 in another set of buckets where then it's available for a variety of analytic services to run queries over. Okay? So this is the example that we're going to be working with. Digging down a little bit, one of the things that we want to do here in our example is we want to organize the data. Imagine you have terabytes, if not petabytes of data. You don't want to just have one big bucket with all your files strewn about. It'd be kind of a mess. It'd be hard to keep track of. And so what a lot of people do is organize this stuff in terms of directory hierarchies in S3. Okay? So that way they can actually manage the life cycle of that data, find that data easily. And more importantly, if you're actually querying this data with Athena or Redshift Spectrum, you can very quickly narrow down the data that you care about and ignore a bunch of other things. So on the left-hand side, sorry, my left and your left too, you see the source data in JSON format. And what we're going to be doing is filtering that data for specific types of events, transforming them into CSV format, and we're going to try to get them into exactly the same hierarchy so that then you can analyze it within a number of other analytic services. This is what the data looks like, and it's a bit of an eye chart, but that's the point, okay? Imagine you have this raw data and you had to come up with a table structure for it so that you could actually query it. It'd be pretty hard. There are about 35, actually more than 35, now 37 event types that GitHub publishes. They have some sort of common structure, but there's a unique payload for every event. And the structure for the payload varies by event type. And so trying to kind of comb through this data to come up with a structure is incredibly tedious, and often people can get it wrong, and it'll break a lot of your analyses. So the first step is to actually crawl this data using the crawler. So what the crawler will do when you point it at this data is come up with this beautiful schema that you see on the bottom left, okay? Over here you'll see 8 columns here. Sorry, this is a little bit dense here. But those are the sort of top-level columns that all the event types share. It detects the data type as well, and if it's a structure, you can actually double-click on that structure, and over here we're showing you the actual complex schema that comes out from unifying all the various payloads across all the different event types that we have. Doing so creates about 200 or more fields. I didn't actually count them all. Doing it by hand, as I said, is going to be too hard. Crawlers also collect a number of other statistics about the data, a number of rows, where the data is, and they also classify the data into what type of data it is, what format it is, whether it has compression, and so on. And that way, if you're using any one of these other services, it knows how to kind of decode that data and start analyzing it. Another interesting thing that crawlers do is at the bottom, you'll notice that we've actually figured out the partition structure and added them as columns to our tables. We know that the data is organized when we're crawling it by year, month, and day, just like the picture that I showed you before. We figured that out, or crawlers figured that automatically. It's not actually information in the data, but it's information in the way it's organized, and we make it available so you don't have to go manage it. And as new data shows up, and new partitions show up, we call them partitions, crawlers will automatically kind of populate that information in the catalog for you. All right, so once you've got this crawled, you can now start converting that data. Basically go to the add job wizard inside of our service, and what it will do is it'll actually give you a schema of the data on the left-hand side that you can play around with. In this particular case, we're only pulling out some subset of the columns that we want for our analyses. In this particular case, ID and type and some payload information. And the arrows basically are things that you can configure yourself to map the source to the destination. And on the destination side, you can play around with the order of columns. You can play around with the types. So you can cast something that was a string into an int or vice versa. You can change the names and the target and so on. And then once you've kind of configured this the way that you want, all on the console, you hit go, and what it does is it generates a script for you. And I'm going to kind of walk through the script for you. I know it's, again, a bit of an eye chart, but I'll kind of describe the individual components of the script and how it works. At the top of the script is just a bunch of boilerplate. It's just stuff that you need to go and get things running, like libraries and context that you have to set up. And the first thing that you do is you actually initialize a thing called a job bookmark. Okay? A bookmark is a way for the script to know where it left off the last time it ran. So it doesn't reprocess all the data and all the state that it had beforehand. It just picks up from where it left off. And I'll talk more about bookmarks and how they work at the end of this talk. The next thing you'll see is a bunch of annotations. They're actually just comments in the code. From the perspective of PySpark, it's just ignored. Okay? From the perspective of Glue and the Glue service, we actually look at those comments, and those comments are what is going to generate the graph on the left-hand side, which describes the transformations from source to destination. The next thing that we do is we actually read the data into a data frame. Okay? A data frame is basically a data structure that represents the underlying data, and it's designed for doing ETL operations. Now, for this particular transformation from source JSON to CSV, the system has decided that it needs to do a certain set of data cleaning transformations and restructuring transformations, and so it's added those things after that. And then finally, when you get the resulting data frame, you write it back out to the destination, which is another sink or a location in S3. Okay? Now, this particular code, if you go run it, what it's going to do is it's going to just transform the data from that source to that particular target format that we did in the previous step, but it's not going to create the Hive-style partitions that we want on the target to be able to go and actually go and do any queries fast. The other thing it won't do is it won't actually do any filtering. It'll actually only do all the projections or pick out all the columns that you want. But if you want to only pick out certain types of events, it's not going to do that either. So you can edit the code right here in the console, but sometimes that's a little bit hard. It's not a tool that you might be used to. So what we offer to you is a developer endpoint, or a development endpoint. What a development endpoint is basically an environment, a Glue-based Spark environment that's set up for you and that's constantly up and running, where you can interactively send your Spark jobs or your Spark scripts to and get your answers back very quickly. And it supports an interface that a lot of IDEs and notebooks are used to. So you can basically attach your IDE directly to the developer endpoint. And then you can start debugging your scripts just like you're normally used to in the IDE that you have. Okay? You can even test it out over example data sets or sample data sets that you have. Beyond just debugging scripts, you can also connect notebooks to your developer endpoint. And when you do that, you get a whole new set of rich functionality. You can start to experiment and explore data sets that you have. At the top, on the left-hand side, what we're showing you is you can actually write PySpark scripts and interactively get answers. In this particular case, we're just showing you schema that's coming back. Or if you register the data as tables in the catalog, then what ends up happening is that you can just use Spark SQL and run SQL commands directly over your data, and then start charting and exploring your data that way. Once you've kind of gotten your scripts the way you want, then you basically upload them to S3 and create or register an ETL job with AWS Glue, and the job basically encapsulates the script. It runs that script for you. Once you've got the job registered with the system, then you can trigger the job based on a number of different conditions. We have several different trigger types or event types that you can trigger a job on. On the left-hand side, what I'm showing you is a way of configuring it to schedule your job at a particular time. You can use a cron expression, for example. You can just run a job on demand. You can also run jobs based on the completion of another job. And so you can actually set up all these very complicated pipelines or simple pipelines of jobs kind of kicking other jobs off with various conditions like ands and ors in there. You can also pass parameters to your jobs so that with triggers so that your jobs have some context when they're running. Finally, when we actually run these jobs, we run them in our service. You never actually have to provision, configure, or manage servers. We give you a serverless interface for running these jobs. And the cool thing is we actually do all the auto configuration that you need to do for attaching to VPCs for getting to your data sources, or getting access based on roles that you have for, say, your AWS resources like S3 buckets. We also maintain the same security and isolation that you would have if you're running these things on clusters in your account. So if you have a job that runs in a particular VPC or with a particular role, it's going to run on a different set of virtual resources than a job that's in another VPC or with another role. So they don't actually intermingle. So your data and your code is separated by those boundaries. You won't be intermingled with other customers or other jobs, even if it's within the same account. Okay? Customers can also specify the amount of capacity that you want to use for a job, and you do that based on this abstract computing unit called a data processing unit, or a DPU. That's how we price our jobs, and so you can basically tell us how many DPU you want to use to go and run a particular job, and we'll spin up those resources automatically for you, and we'll automatically scale those resources. And then finally, you only pay for the resources that you consume. We've now gone to per second billing, and we still have a 10-minute minimum for all of your jobs. Okay. All right. Well, so now you know how to get a script running into production and what happens underneath. What happens if you want to go and customize your script? What are all those things, those bookmarks and dynamic frames doing? Well, to try to understand that, we need to first kind of get into what Spark is and how it works. Okay. Apache Spark, if you guys aren't familiar with it, is a parallel scale-out data processing engine. It's got fault tolerance built in, so if things fail, it restarts your jobs for you internally. And then we also have another layer of restarting and so on. More importantly, it's got a flexible interface. You can not only write scripts, but you also can do SQL with Spark. And you can actually intermingle these things freely. So it's actually quite flexible. There's a rich ecosystem of use cases around machine learning. People are doing graph analytics with Spark. People are doing SQL analytics. They're doing ETL with Spark. They do a lot. At the core of Spark, what they have are these data structures called RDDs. They're basically collections of data that are resilient, or resilient data set, distributed data sets. That's what they stand for. And then on top of RDDs, they've built these things called DataFrames, and on top of DataFrames, they have a whole bunch of transforms that are basically SQL-based transforms that Spark SQL offers. Well, what we've done is we've built an analogous set of libraries that work with all of this code. We have these things called DataFrames, and I'll talk about that next. And our Glue ETL libraries on top of DataFrames allow you to integrate with all of the other AWS Glue components, like data catalog, orchestration or scheduling, code generation, bookmarks, as well as integrate with other AWS services natively, like S3, RDS. And we have more ETL transforms, connectors, and formats that Spark SQL doesn't. We also have this new data structure called dynamic frames, and I want to get into that next. To kind of understand how dynamic frames work, we first have to explain how DataFrame works. DataFrames are the core data structure for Spark SQL. They're like structured tables in a database system. You kind of need to have the schema defined up front for DataFrames. Okay? Each row in a data frame has the same structure. And so what this means is if you're trying to load data and you don't know the schema, data frames have to first read all your data and compute the schema, and then they can bring it in. So you have to do 2 passes over your data. The beautiful thing about this is that if you're working over structured data, especially data that looks tabular, and you want to do SQL-like analytics, this thing's perfect for doing that. But for ETL, so it's not quite ideal. And so what we did is we introduced dynamic frames that relax some of the assumptions about having a schema up front and having the same structure per row. They're like DataFrames, but designed for ETL. They're designed for processing semi-structured data. So what do I mean by semi-structured data? The data that I showed you earlier, the public GitHub timeline. You got lots of different event types, and the payload structure varies by each different type of event. Okay? And so what ends up happening over here, I'm going to show you how we actually represent this data in dynamic frames. What dynamic frames are basically a collection of dynamic records. Okay? And I've given you sort of a cartoonish version of the public GitHub timeline where you have 3 different event types: a create event, a push event, and a pull event. The top line there, ID and type, is shared amongst all of these events. And the bottom line, the payload, is actually different and very different from event type to event type. For a data frame, if you wanted to store all this information, you'd have to have a structure that's sort of the union of all of these structures. And so you'd have a lot of columns or fields that would be empty. Okay? And so it would look a little bit like the shape at the bottom. For dynamic frames and dynamic records basically are self-describing. So you don't actually need to have a schema up front for storing this inside of a dynamic frame. Each record actually stores its own schema, and so it can vary from record to record to record. What this means is it's really easy to do a whole bunch of restructuring transforms, modification transforms, and in some cases, or in many cases for semi-structured data, this representation can be more compact than a data frame row. And an interesting consequence of all of this, of course, is that many simple flows, or even complex flows, as long as you don't force a schema computation, can be done in single pass. So if you have terabytes of data that you want to convert, petabytes of data that you want to convert, you don't have to go over it twice. Another thing that I want you to note here is that I've done something very subtle here. The IDs in the first 2 records are strings, and the ID in the 3rd record is actually an integer. Okay? Spark will basically read that and just convert it to whatever it thinks it should convert it to. But you may not want that. Well, data frames, because each record is sort of, self-describing, we keep that intact. And then you can decide later on what you want to do with it. So in the dynamic frame schema here at the bottom, you'll see on the left-hand side, there are 2 different versions of ID, one that's an integer and one that's a string. All right, so what can you do with dynamic frames? Well, we have over 15 transforms and adding more and more. One of the simplest things that you can do is you can decide how you want to resolve your choice between integer or string. And by the way, you can have all kinds of choices. You can have a choice between a string and a struct, an array and a string, and so on. And it's not so easy to decide what to do with a data frame, right? Are you going to stringify it? Are you going to array it? Here, you get to actually specify what you're going to do through the resolve choice transform. It's a cool little transform. You should try it out. Another one, which is kind of a superset, lets you resolve choices and do a lot more things like restructure, is apply mapping. Okay? So apply mapping will allow you to take structured or semi-structured data or nested data and flatten it in any way you want, pick out the columns that you want, rename. It basically implements that mapping that we saw on the screen. And you can actually go backwards as well. You can go from a flat structure to a nested structure. A third, and so one of our most complicated and most interesting transform, is Relational Eyes. We tried to actually originally build Relational Eyes with data frames, and we found out that it was really hard and very inefficient. What it does is it takes any arbitrary schema that you have in a semi-structured schema and turns it into a collection of tables and columns so that you can load it into a data warehouse without the need for support for various choices or without having to have support for arrays. What we do is we basically create a column for every path from the root to the leaf, and for every array, we separate it out into an auxiliary table. That auxiliary table will have multiple elements for that array, and it'll join back up with the original table using a primary key, foreign key relationship, okay? And the relationalized transform does this on the fly as it's seeing the data come through, right? It's pretty cool. It adds new columns and types and tables on the fly and will load it into Redshift. It tracks the keys and foreign keys so that you never duplicate those keys again. And it's interesting, by actually flattening the data and making them columnar and putting it into a columnar data warehouse, which is designed for handling columnar data, your SQL queries now can go basically orders of magnitude faster than if you were just natively processing the JSON data with one of these other analytic services. There are a bunch of other useful transforms that we have. 2DF converts a dynamic frame to a data frame. So if we don't have a transform we don't have a transform that you need, you can convert it to a data frame and just run your transforms in Spark. We have spigots. You basically insert them in your flow, and then you can get samples of your data that are flowing through into S3 so you can debug. We've got unbox, which will take a column and parse it. So for example, if you have a JSON column in CSV, you can unbox that column and start querying that. We've got a bunch more. You should try it out. So what's the bottom line here? Well, it turns out that we can go fast because of this. Remember I told you that we only have to do one pass? Here's a workload where we convert that JSON to CSV, that GitHub timeline data. We filter out for just the pull events, just the events that are just, where people are talking about pull, okay? And then we write it back out in CSV. And whether we're converting a day, a month, or a year worth of data, on average, we're basically getting 2x the performance of native Spark, just vanilla Apache Spark, okay? Now, if you're forced to compute a schema for whatever operation that you want to do, we're going to go about as fast as Spark does as well. So we're not really losing a lot of performance, and in these particular cases, you actually gain a bunch of performance. Another thing that we do is we have some optimizations for dealing with streaming data. So imagine you have data coming in from Kinesis Firehose. This data comes in sort of sporadically. That's what streaming data is like. And so you'll end up with a lot of small files that are empty or just a few records in there, and then you'll have files with some big, lots of records in there. And it turns out Spark right now has a lot of overhead per file. It schedules a task per file, and the result of that task is all those tasks is sent back to a central master or a driver. And so if you have hundreds of thousands, if not millions of tasks, and they're all really small, the scheduling overhead is high for doing that work because you're kind of communicating for doing very little work. And there's memory overhead for keeping track of all the results, which are basically null, right? And so as you scale the number of partitions and number of files, in this particular case, we're actually going over Twitter data, okay? At some point, Spark basically just poops out. It just doesn't have enough memory to keep going. And at around 320,000 files, 160 partitions, we're going about 7 times faster than Spark. Vanilla Spark, that is. Okay, 2.1. Why are we able to do this? One, because we integrate with Data Catalog, and so we have a fairly good idea about all of the partitions and their structure, so we don't actually have to go and scan through and list all the files and create partitions and so on. Another thing that we do is we also have a bunch of statistics about those files, how many there are per partition. And so what we can do is we can actually group those files per task. So you can have multiple files handled by a single task, and so you don't overwhelm that coordinator. And as a result, we can get to about over a million files in this particular example. And we probably can scale further. We just didn't finish the experiment to see how far we could go. All right, so that's dynamic frames in a nutshell. I encourage you to go and try them out. Now I want to kind of switch gears a little bit and talk about bookmarks. Remember I said that there are these things called job bookmarks that let the script, when you're running from one iteration to the next, remember what happened? That's what a job bookmark is. If you're trying to periodically run a job, for example, you want to go and process one partition, 1 day's worth of data at a time. You don't want to reprocess all the input just to be able to go and process the next day's worth of data, right? You want to remember what you process so that the next day you can process just the new stuff. More importantly, you don't want to also duplicate the output over and over again. Now, you can kind of build this stuff by hand, right? You can kind of, come up with ways where you look at the timestamp and, the time of day it is, and kind of come up with a partition that you want to go and process. But again, it's brittle. If you ever change your partitioning structure, it won't work, and you have to go and, change all of your scripts again. So what we offer are bookmarks, and what they do is they basically keep track on a per job basis of the state of the previous runs. They're basically per job checkpoints. They persist the state of all the readers or sources in your script, the state of transforms, and the state of all the sinks or the targets in your script. Some of the things that you can do with job bookmarks is process files on a daily basis for our GitHub archive example. You can process Kinesis Firehose data on an hourly basis. It looks very similar. You can track timestamps on tables and databases or primary keys to see which rows you've already consumed so that you don't reconsume the same rows. And you can also track the keys and foreign keys that you generate when you normalize your data, in particular for the Relational Eyes transform. You can also play around with bookmarks where you turn them on and off. Of course, when they're turned off, what you're doing is just basically, when they're turned on, what you're basically doing is just advancing the state of your computation. When they're disabled, you might want to do this just to kind of debug your script to see what's going on, right? We don't actually look at the bookmark information, it's just ignored, and you just process your entire table. There's a third option, and it's a cool little option, which is called pause, which means go back to the previous run, rerun it, but don't advance the state. And you might want to do this, for example, if one of your runs broke and you wanted to see what the output looked like without having to kind of advance the state by yourself. So it's a debugging trick that you can use. How does this all work? Well, we could keep track of all and every file that we have run for every job and make sure that you don't look at those files again. But that's going to be very complicated, and it's going to require a lot of state. So we got to avoid that space blow up. The simplest way to do that is to use timestamps to filter out previously processed input. So imagine you're on run number 2 over there, and run number 2 started listing all your files at T2, and then processed them. Then on the next run, only the files that were created after T2 are the ones that you need to look at, right? Those are the new files. And because S3 files, they can't be modified, you can look at the timestamps and say, you know exactly which ones are the new files. So that works in most of the cases, okay? Especially when S3 behaves in a strongly consistent way. But it doesn't work every once in a while when S3 becomes an eventually consistent system, because you can actually have files appear in the next run that you didn't see in the previous run, even though their timestamps are older, than when the previous run started. So what we do to deal with this inconsistency is we actually keep track of all the files that we saw in an inconsistency window right before the previous run listed all those files. Right? We keep a sort of a small delta, and that's configurable. And that's basically an exclusion list of files that we keep track of that you can filter out the next time you run. In the subsequent run, you basically start listing all your files from the previous timestamp minus this delta, this consistency window. These are all the files that you list. And then you eliminate the files that you've already seen, but keep the files that you haven't seen, and you process them. And this works really well. And this is pretty complicated to get right. You don't want to be building this yourself, and we provide that underneath for you. And this is just for sources. We do similar things for transforms and sinks. All right, so I'm going to wrap it up now. I've shown you the 4 easy steps that you need to build a production ETL flow. I've described dynamic frames and job bookmarks and how they work. And hopefully, with this knowledge, you can go and actually build your own scripts now and get going with Glue. I want to make 2 additional announcements. One, we're soon going to have Scala support. So all your scripts that are in Python right now can do a lot of orchestration, sort of, building these pipelines, but a lot of the heavy lifting that you need to do to process your data often needs to be done in Scala, and now you're going to be able to do that with the Scala support. There's also 2 new regions that are coming up, Asia Pacific, or Tokyo, and Ireland, so you can run your jobs from there. All right, with that said, I want to hand it over to Keith, who's going to describe how he used Glue to get Merck started very quickly and easily. Thank you.
So, good afternoon, everyone. My name is Keith Lola. I come to you from Merck. Outside the U.S., we're actually known as MSD. So, for those of you who come from outside the U.S. So, we actually started looking at Glue, I think, the day it was announced, the day it was made public. And one of our biggest challenges was trying to get all the ancillary data we needed for our enterprise software delivery management system up to the system itself so that it can be used. And for those of you that maybe don't come from a large enterprise, the system that we use helps people do things like environment management, to understand, what makes them up, if they're available in the life cycle, so maybe they want to use them during one of their projects or things like that. So it actually does a whole bunch of other stuff like deployment planning and scope management, but I'm here to talk about Glue. So our challenge started with, we didn't have many integrations at all with our enterprise system. We had a lot of the BI teams that wanted access to this, to the data in the software delivery management system itself, plus the data that we were going to take and actually align it to the context of an application. And these projects, as most people probably recognize, a project has a certain time frame. They want it now. The system they were using to deliver it, we needed to get it somehow from the raw state and up to the system itself so they could use it in a relatively short time frame. So this brings us to a summary of our challenges. So we had this short timeline to get this data layer together. So my team and I were a little bit of not troublemakers, but we like to push the envelope. So when I saw something like Glue, and we had the opportunity to actually get a data layer together for our system, it certainly seemed interesting. The one thing that you have to recognize about my team is we are not ETL developers. We work with a lot of the project teams that do ETL development and the different technologies inside the ecosystem, but we are not pure developers. Most of us have some sort of background in our education or prior experience where we've done some coding. Additionally, the only support that we really had available, because we were using Glue the day after, so our cloud services team helped us get it connected the day it came out, set up in our enterprise, and then I probably started pinging Mehul and his team on a Wednesday, asking about some individual questions and things. But from there, it was interesting because we started exploring a lot of our data that we needed to bring in. And as you can imagine, we're an enterprise company, and we've been around for, I forget what the slide says, over 100 years, let's just say. So we have a lot of legacy systems. We have even, I think, some mainframe, but probably not. So you can imagine the different amount of data that we needed to bring in to align to an application. And it was definitely a different, people had it in spreadsheets, they had it in team sites, they had existing databases, and we have a CMDB system, of course. So one of the things I started with and looking at is hoping that I can find some way not to have to move the data. Because everyone typically takes the data and wants to warehouse it, but then we have multiple copies of the data everywhere. So when I saw we had an easy way to actually catalog the data, we started pushing to that avenue a little bit more. But because because we have a lot of legacy systems, we had to keep the warehousing option available to us. So what we came up with was, and by no means was this something that we started day one. We did take a very step-by-step approach. What our backend system, our data layer actually looks like now is here's where we have a number of our different sources, whether they're coming from the team site or whatnot. We have a Lambda function that'll prepare it and drop it in the S3 bucket. We do have some local DBs, and then we have some databases that run in RDS. So the key for us was being able to get all this into one place. And the glue crawler, I think actually on a Wednesday, we were already moving data. We had some raw data files. We had some data files here. And the very first thing we did was what Mayul showed you in the presentation. We set up a crawler. We let Glue make the script, and we sent it to a database, just so we could see how everything was moving forward and try to understand the transforms. Because, as I said, like, my team's not developers, so I do have some teammates in the room, Rajesh, Brian, and Jeff over here, and Rajesh was really good with stored procedures. He can do wonders with a stored procedure. So we pushed it through day one and said, let's see what a stored procedure looks like. So the glue crawler, I did that. My team wasn't ready. We didn't have a lot of resources available. I did that myself. I do have a little bit of a development background, but as we grow up through the enterprise, I'm now more in a leadership position. So once we had the crawler in place to update the catalog, then we started to understand a little bit more about that. So the day one first run was basically just getting that one script over to Glue. And we established an RDS database so Rajesh can do his establish a stored procedure. But what we've done from there is we've taken those stored procedures and we've eliminated them and started just doing it right in Glue, right in the PySpark script. We have extended it just back to Python, just trying to leverage some of the PySpark libraries itself. So from here, then, we'll use the Glue transforms and leverage the catalog. We have done some calculated data and transactional data from the source, so we're actually adding on to the data because how it relates to the end solution. And then we have a Lambda function that'll then send it up to our enterprise software delivery management system. So the one thing you'll notice here is we recognize that our BI teams, so here's how we give the BI teams access to this system. So after we feed the enterprise delivery management system, well, actually in parallel, they have access to read the RDS database. But what we're trying to help them with is actually just reading the catalog itself. So they have access via their BI tools to use the same catalog everyone else does. Because ultimately what we do anyway is the crawler is actually just reading the catalog and is actually just reading the RDS database and updating the catalog. So we provide the option to use the RDS database at this point more from a legacy aspect. So for us, being able to leverage the existing resources was important. Finding something that was quick and easy to use, that was important. In Glue, it's pretty easy to use, and from what I can see, there's a lot you can do with it, even extend it beyond. We didn't have to set up a single server, and we didn't have to go to a single shared service to ask them, to write code for us or provide requirements for them to do that. So our timeline was really short. We were inside of a week moving the data through to our system, and since then we've just been perfecting it to make it faster, to do more in line and less in the database itself. Adapting to new data sources, this was an interesting one. So my manager actually gave me a new file from a part of the company and said, here it is, how long is it going to take you? I said, about 15 minutes. He said, I'm going to tell him an hour. I'm like, 15 minutes? It's going to take me 15 minutes. But, you know, it's actually really easy to move it through. So now we have a single source of data. We're on our way to make it more of a data lake, and getting people to actually utilize the catalog is key to that. So I can get rid of the RDS database and look at something maybe like DynamoDB is what we're looking at next. And the biggest win for us was our projects got what they wanted. So they got extended data about their environments and about their applications that came from multiple different sources, and they can see it in one place, and they can focus on managing their application and not having to manage, you know, moving the data around. So Glue for us was an interesting timing, offering at the right time, and from where I can see, you know, sky's the limit. So, thanks.